So for number 7, we have a function here, this polynomial, and we're on the interval 1 to 4. So what we want to do is we want to find what is the possible maximum area and possible minimum area that a function could have on an interval. So what basically this is asking is, if we have a polynomial and we have a specific interval, it's going to curve some way in that interval. But the maximum area that it would have to be bounded by, it would have to be less than always, is if we had some function like this, and let's say we're going from here to here, it would always have to be less than if we made a box where we used the maximum value of the function as the height, and then went like this. So in other words, the area is fully contained in that box. That's the upper bound, the upper estimate for the area. The opposite idea of that is the lower bound. So whatever the minimum value of this function is, which let's say is over here, if we drew a rectangle, we'll do that one in a different color here, like that. So we drew a rectangle that still covered the same width, the same interval, but its height was the minimum of the function. The area that this function covers has to be bigger than this green rectangle always. So think of it like this. If our function was a horizontal line, then it would be exactly one of the max or the min. Like, we would know that it's that. But since this is some polynomial that has a lot of curves in it, we can, if we didn't want to calculate the area exactly, we could surely say that it's in between the area that's made by the maximum of the function and the area that's made by the minimum of the function. So finding out those areas is relatively simple. All we need to know is the min and the max of the function. So we want to say, what is the max value of this function? What is the min value of this function? Only on this interval 1 to 4. That involves doing the derivative. So f prime of x, our derivative function here is going to be 6x squared minus 38x plus 52. And this part would be 0. So we want this derivative to equal 0. And that way, we would get our critical numbers. We can factor out a 2, and we get 3x squared minus 19x plus 26. Again, we're saying this equal to 0. So it might not look like it immediately, but this is factorable. So one of these is going to have to be 3x, one is going to have to be x. The factors of 26 that we want here are 13 and 2. And we want the 2 times the 3, and they both have to be subtracted. So this would give us a positive 26 constant, which is what we have. We get minus 13x minus 6x, which is minus 19x. And our first term is x squared. So that's equal to 0. So what values of x does that give us? This one would be 13 over 3, and this one would be 2. So those are the two critical numbers of this function. But remember, we're only interested on the interval 1 to 4. Well, 2 is clearly in 1 to 4, so that counts. 13 over 3, well, that's bigger than 4 because 12 over 3 would be exactly 4. So we don't want this one because it's out of our interval. So we found that the only critical number on the interval 1 to 4 is at x equals 2. So now to find the min and max of this function on the interval, we need to do our absolute min and max. So we need to check what is f of 1, what is f of 2, and what is f of 4. Because those are the endpoints of our intervals and the critical numbers in between. So remember, we want the absolute lowest value that this function has and the highest value on the interval. So those could be endpoints, like it is on the lowest one here. Or it could be a critical number that's in the middle. So that's why we do this like absolute min and max. So let's plug in our numbers and figure this out here. With 4, it's going to get kind of big because of these constants. Remember that if you had this problem on a test, it would all be in numbers that you could deal with a lot more easily. So if we plug in 1, well, that one, we don't really have the powers here, so that's not a big deal. So all these x's are just 1. So we would get 54 minus 19, which would be 35. 35 minus 29 is 6. So if we plug in 1, excuse me, we would get 6. So if we plug in 2, let's see what we would get here. So I'm plugging in 2 for x. Plug in 2 for x, we get 15. And if we plug in 4 for x, we would get 3. So those are our values, our y values. So you can see here, we get an absolute minimum when x equals 4, and that minimum is a y equals 3. And we get a maximum when x equals 2, which is a y of 15. So we're almost done answering the question. So then the problem is, if we know now that our max value is 15 and our min value is 3, those are the lowest and highest y values, what are those areas that they bound? Well, these are just rectangles that have height of 3 and height of 15. Their widths are the same, though, and the width is the width of the interval. So our interval went from 1 to 4, so these rectangles have width 3. So in other words, that means the area, which is the definite integral from 1 to 4 of f of x. Actually, let me write this over here because we're going to write it as an inequality. So that expression means the area under f of x between 1 and 4. We know that has to be bigger than or equal to the area of the small rectangle, which would be 3 times our width, which is 3. So it has to be greater than or equal to 9. But it can't be bigger than our big rectangle, which is covering the whole possible area, which is our height 15 times our width, which is 3. That's 45. So without actually calculating the area of this function, we know it has to be in between 9 and 45. Which doesn't sound like it's that good of an estimate. But for certain functions and certain intervals, this could provide a useful estimate.
The Teaching Center, UF's Learning Resource Center.